Hey students, welcome back. In this video for our elementary statistics course, we're going to be focusing on section 4.2 of our textbook, which is about the addition rule and the multiplication rule. Okay, so when you're watching this video, make sure you've already mastered section 4.1, which includes the basic concepts of probability. So make sure you watch my lecture from 4.1 and also done your quizzes and homework if you're in my class. Okay, so 4.2 is a big section. I'm hoping to do this entire video in one shot, but it's probably going to be a long video, so I might break it up into two parts, but we'll see. So what are we going to be learning in this section? Well, first of all, we're going to learn the basics of the addition rule, which is a tool for finding the probability of a compound event, A or B. That's the probability that either event A occurs or event B occurs, or they both occur as a single outcome of a procedure. The word "or" in the addition rule is associated with the addition of probabilities. Okay, and we will also use the addition rule to learn another important probability formula known as the complement rule. Okay, and then after we get through the addition rule and the complement rule, we'll also be learning about the multiplication rule. Okay, so the multiplication rule is used for finding the probability of a compound event of the form A and B. Okay, which is the probability that event A occurs and event B occurs. In other words, the probability that both events occur. Okay, and the word "and" in the multiplication rule is associated with multiplication. Okay, and then the only thing to keep in mind is, even though they're called the addition rule and the multiplication rule, after we're done with this section, we will be doing examples of problems that actually involve a table. And when you're working with a table, the addition rule and multiplication rule can be useful in some situations, but not in others. So we'll see lots of examples of all that. Okay, so let's get started with, before we do either rule, we need to talk about a compound event. Okay, so a compound event is any event combining two or more simple events. So remember in 4.1, we said that a simple event has to involve only one outcome. If it's not a simple event, it's a compound event, okay, automatically. So any event combining two or more outcomes is a compound event. And if you look at the word compound, it sounds like combine, which means you're combining, two or more outcomes. Okay, and the reason we're learning about that here in this section is there are different types of compound events. But for starters, we're going to be learning compound events of the form "or." Okay, so when they use the word "or" in a compound event, we would write the probability of A or B. A would be the first event, B would be the second event. And what this notation means for the addition rule is the word "or" just tells us that the probability, we're finding the probability that in a single trial, event A occurs, or event B occurs, or they both occur. Okay? Which can seem like a lot of different cases. It really is quite a few different cases. But the reason it's called the addition rule is essentially what you're going to be doing is you're going to be doing probability of A plus probability of B. So when they use the word "or", essentially just remember that "or" means or means add. Okay, so that's roughly what it means. And then in our book, they have two versions of this addition rule. The first version is a little bit easier to understand. The first version is called the intuitive addition rule. So like I said, the word or basically just means you add. So to find the probability of A or B, add the number of ways event A can occur and the number of ways event B can occur, but add in such a way that every outcome is counted only once. In other words, we have to avoid double counting. Okay, the probability of A or B is equal to that sum. Remember that in math, sum means add. Okay, divided by the total number of outcomes in the sample space. So hopefully you're already used to dividing by the total number of outcomes in the sample space because we went over that in detail in section 4.1. Okay, so intuitively, or just means add. They call this intuitive because they don't have a formula here. Now, the formula looks a little bit more intimidating, so let's look at it. So the formal addition rule is that the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, where the probability of A and B denotes the probability that A and B both occur at the same time as an outcome in a trial of a procedure. So they don't use pictures in our book, but I would like to give you a picture here, which is a Venn diagram, because I've always found a Venn diagram to be helpful for understanding this rule. So if you look at, even if you've never seen a Venn diagram before, I think you can understand what I'm talking about here. So if I make this first circle, the interior of this first circle be the probability of event A, okay, P of A. And then I draw another circle that overlaps with the first circle. And in this second circle, we're calling that the probability of event B, or P of B. Then the probability of A and B is what they're subtracting here. And that actually refers to the overlap here in the middle. Okay, so this overlap right here in the middle between these two circles is the same as the probability of A and B. Okay, so probability of A and B is the overlap. Now, the whole reason I bothered to draw this picture and the reason I find this picture helpful is if you look at the formal addition rule, we're adding the probability, so we're adding P of A, which is this green circle, plus P of B, which is this orange circle. But the problem with just adding P of A plus P of B is that we're actually double counting this overlap. Okay, and the probability of A and B is the overlap. Hopefully you can see that we're double counting it, because if we do P of A, we've got all of this, so we're counting this once. And then when we add P of B, we're doing all of this circle, so we're counting this twice. So because we're double counting the overlap, that's why we have to subtract the overlap. So we have to subtract the probability of A and B. Because we are double counting that middle part, that's where this formula comes from. Okay, and of course, if P of A and P of B don't have any overlap, then this probability of A and B is going to be 0. Okay? So I always found this picture helpful, which is why I took class time with it. You may or may not find it helpful. But that's where the addition rule came from. And then they don't have a lot of good examples on the slides, but we're going to be doing a bunch of examples after we get through the slides. Okay, so let's go ahead and go on to the next slide while I erase this. So with the addition rule, I gave you the formal addition rule, which basically just said you add probability of A plus the probability of B, and then you subtract the overlap, probability of A and B, in order to avoid double counting. So I want to talk about this slide here. So disjoint events are special types of events. So if event A and event B are disjoint or mutually exclusive, that means they cannot occur at the same time. In other words, disjoint events do not overlap. Okay, so if you're doing your homework or your quiz or your exam and they ask you whether two events are disjoint, another way of saying it is they have no overlap, or if events A and B are disjoint, that would mean that the probability of A and B, because there's no overlap of the two circles, the probability of A and B equals 0. All right, and it should kind of make sense, even though I haven't drawn the picture yet. If I go back to the Venn diagrams with the circles, if there's no overlap, the probability of A and B equals 0, then we're going to our picture is going to be two circles, P of A, P of B, but there'll be two circles that don't overlap. Okay? And why are they called disjoint? Well, if you look at the word disjoint, it kind of sounds like disconnected. And disconnected is really what the picture looks like here. So we've got P of A and P of B don't have any overlap, so they're disconnected or disjoint. Okay? So hopefully that helps to have a picture, because they don't really have a picture in our book. All right, so some examples of disjoint events. Disjoint events. Event A, randomly selecting someone for a clinical trial who is a male. Event B, randomly selecting someone for a clinical trial who is a female. The selected person cannot be both. Okay? I mean, I guess you could make the argument that here they're talking about sex. They're not talking about the gender that people identify as. But you could also argue that even with sex, some people are born as hermaphrodites, so they would be both genders. But in the book, they're ignoring that. They're ignoring hermaphrodites, just for the sake of an example. So the reason these events are disjoint is simply because in the book, they're assuming that someone cannot be both male and female for their sex at the same time. But it's just an example. So it's just an example of two things that can't happen at the same time. Cannot be both. Okay, so what are some examples of events that are not disjoint? Events that are not disjoint. Event A, randomly selecting someone taking a statistics course. Event B, randomly selecting someone who is a female. Okay, so these are not disjoint events because someone taking the statistics course can also be female, right? So because they can be both, these events are not disjoint. And if you imagine the picture, people taking a statistics course and people who are female will have overlap, right? And that overlap isn't 0. and because the overlap exists, that means the events are not disjoint. All right. Cool. So hopefully that helps. And then here's a summary of the key points of the addition rule. Okay. So like I said, we haven't really done a full example yet, but there aren't a whole lot of good examples from the book. So we're going to be focusing more on examples from your homework that I'll be doing after we get through the slides. To find the probability of A or B, first associate the word or with addition. To find the value P of A or B, add the number of ways A can occur and the number of ways B can occur, but be careful to add without double counting. And to avoid double counting, if you can't be careful about it, then you just go back and use this formal addition rule. Okay, so if you just use the formal addition rule, this will always work. Whether the events are disjoint or not, just keep in mind that for the formal addition rule, if the events are disjoint, that means this probability of A and B is going to be 0. So for disjoint events, you can just add the probabilities and not even worry about the overlap. As long as the overlap is 0, then you're just going to be adding the probabilities. So just a real quick example of the formal addition rule that I'm going to come up with on the spot here. Okay, so we're just going to look at disjoint events. Okay, so example, roll a fair 6-sided die. I'm just going to say roll a die. So when you roll a die, that implies that it's a fair 6-sided die. Okay, so find, let's say they asked us to find the probability of rolling a 2 or a 5. So we already know how to do this without the addition rule from the previous section. But here, if we want to find the probability of a 2 or a 5, we can use this addition rule. So the addition rule just says that you replace or with plus. Okay? And now, before we do that, I want you to think about these events. So rolling a 2 and rolling a 5, are these disjoint events or not disjoint events? Think about that for a second. Feel free to pause the video if you want to think about it, and then unpause it when you think you have your answer. Okay, and the answer is these are disjoint events. Why? Because you can't roll both a 2 and a 5 in a single roll. So when they say roll a die, they mean we're only rolling a single die and we're only rolling it once. So you can't, on one roll, you can't have both a 2 and a 5, so these are disjoint. So what that means is we can literally just add the probability. So this is going to be the probability of a 2 plus the probability of a 5. Okay, and you could write, if you use the formal addition rule, you could write minus the probability of a 2 and a 5. But the thing is, that's really not necessary here because the probability of rolling both a 2 and a 5 on a single roll, it's impossible, right? So that's equal to 0. Okay, so that's why I didn't even bother to write that, because this minus 0 isn't, subtracting or adding 0 doesn't do anything. Okay, so we just don't write it. So the only reason that overlap is 0 is simply because rolling a 2 and rolling a 5 are disjoint events. Okay, and then if we add these probabilities, remember that the probability of a 2, because it's a single outcome, is going to be 1 divided by the total number of possible outcomes. Well, it's a 6-sided die, so there are 6 possible outcomes. So that's going to be 1/6 for the probability of a 2 plus 1/6 for the probability of a 5, because once again, rolling a 5 is a single outcome. So there's one outcome in our event divided by 6 possible outcomes. Okay, so the probability of a 2 or a 5 is 1/6 plus 1/6. And remember, if you're adding fractions that have the same denominator, you just add the numerator. So we're going to do 1 plus 1 is 2 over 6. Okay, so this gives us 2 over 6. And then we can simplify this fraction by dividing the top and the bottom by 2. Okay, so that fraction actually simplifies. After we divide the numerator and the denominator by 2, it simplifies to 1/3. Okay, so 1/3 is the probability of rolling a 2 or a 5 on a single roll for a fair 6-sided die. And remember, once you have your fraction like this, 1/3, you can go ahead and type it into your calculator. So let me grab my calculator. So I do 1 divided by 3, and that'll give me a decimal. Okay, so 1/3 as a decimal is 0.333. I went ahead and rounded it to 3 decimal places, which is what they usually do. They usually round probabilities to 3 significant digits. Okay, and then if you want to interpret this even more, you can convert this probability as a decimal into a percentage. So if we move the decimal 2 places to the right, that gives us a percentage, which is going to be kind of running out of room here. So let me write a little bit smaller down here. That's going to give us 33.3% chance. Okay, so 33.3% chance. But this should be making a lot of sense, because if they weren't using the word or, it would be a different situation. But if they're using the word or, it makes sense that you add the probabilities, and because you can't roll both a 2 and a 5 at the same time, it makes sense that 1/3 of the time you're going to roll either a 2 or a 5, because that's 1/3 of the numbers on a 6-sided die, right? Because a 6-sided die has 6 possible outcomes, so 2 out of 6 is the same as 1/3. Okay? And I know that example was very straightforward, but I like to do some easier examples just to get the concepts down, and then we'll do some harder examples after we're done with these slides. Okay? So let's return to the slides while I erase all this. So we've gone over the addition rule. Now I want to talk about complementary events. This is a topic that we've already mentioned in section 4.1. Remember that A with a horizontal bar above it indicates the event where A does not occur. Okay, so when we write A with a horizontal bar above it, the way most people would read this is they would say not A. Okay, so we use not A to indicate that event A does not occur. All right, common sense tells us this principle. We are certain with 100% probability, remember a probability of 1 means 100% chance, that either event A occurs or it does not occur. Okay, so what they're saying here is the probability of any event A, the probability of the event A or not A has to equal 1. Now, why is that true? Well, I'm gonna draw another picture real quick here, but it follows because the event A and the event not A are disjoint. So the probability of A or not A equals P of A plus P of not A. And when you add those up, it has to equal 1 because 100% of the time, when you're doing a procedure, either event A has to occur or event A does not occur. So it either occurs or it doesn't occur 100% of the time. So an example of that would be if you're flipping a coin and event A is flipping heads, well, 100% of the time, you're either going to flip heads or you're not going to flip heads. So if you do 50% chance of flipping heads plus 50% chance of not flipping heads, 50% plus 50% is 100%. And remember, 100% is the same as a decimal of 1. Okay, so hopefully that makes some sense. And then, like I said, real quick, I do want to draw a picture describing this. Okay, so going to this next slide, these are different formats of the same equation that we had on this slide. Probability of A plus probability of not A equals 1. For these different formats, the most popular one would be this one in the middle, but you can use any of these three formats. Anyway, like I said, I want to draw a picture here. So let me switch to just my camera. So if we draw a picture here, we can draw event A, P of A, as the area inside this circle. And then if we consider all possible events in our sample space, then the probability of event A would be the interior of the circle. The probability of not A would be everything except for the interior of the circle. So probability of A complement, or not A, would be actually everything else besides the circle. So just from the picture, we can see that P of A, which is the inside of the circle, and P of not A, which is the outside of the circle, are disjoint because they have no overlap, right? So they have no overlap, but if you do P of A plus P of not A, it gives you everything inside of the entire rectangle. Okay, so that tells us that P of A, which is this part, plus P of not A, which is everything else in the rectangle, has to give you 100% of the rectangle. And remember, 100% is the same as a decimal of 1. Okay. And the main reason I'm drawing these pictures is I always found them helpful just for understanding these concepts. But not everyone's a visual learner, so you may or may not find the pictures helpful. Okay, but that's the picture that describes what's going on here. Okay, so going back to the slides, for the rule of complementary events, like I said, there's three formats. The top equation was the one that I just showed you. But when you're actually using the complement rule or the rule of complementary events, like I said, the middle formula is going to be the one that you usually use. Okay, so this middle formula right here is the most useful in most situations. Okay, so probability of A complement, or probability of not A, equals 1 minus the probability of A. So because that's the one that we usually use, I'm going to go ahead and write it down here because we're going to need it on the next example. So probability of A complement, or not A, equals 1 minus the probability of A. Okay, so let's see this rule in an actual example. I do like this example from the book, which is why I'm using this example. Okay, example on a smartphone home. Based on survey results from the Consumer Technology Association, the probability of randomly selecting a household in the United States and getting one with a smartphone is 0.87. Now this was the time that the book was written. It's probably a lot higher than that at the time that I'm making this video. It's probably closer to like, 97% or 98%. 0.87 is the same as 87% if you move the decimal 2 places to the right. Okay, but anyway, we're using the data that they have from the book, which is dated. Okay, so the probability of a smartphone equals 0.87, or 87%. And then their question for us is, if a household is randomly selected, find the probability of getting one that does not have a smartphone. Okay, so here we can just directly use this form of the complement rule. So we already know the probability of a smartphone is 0.87. So using this format, we can write this out. So probability of getting a house that does not have a smartphone, we would write probability of smartphone, and then we would write a horizontal line above the word smartphone, which means the probability of not getting a smartphone equals 1 minus the probability of having a smartphone. Okay, so that's just the rule of complementary events. Here our event A is having a smartphone. So the probability of not having a smartphone equals 1 minus the probability of having a smartphone. Okay, and then we can just directly plug in the probability that they gave us. They told us that the probability of having a smartphone is 0.87. So we just do 1 minus 0.87. So in our head or on our calculator, that gives us a decimal of 0.13. And then if we move the decimal 2 places to the right, we can write it as a percentage. So that is a 13% chance. Okay, so 13% chance at the time that the book was written in that survey, from the people in that survey, there was a 13% chance that a random household wouldn't have a smartphone or did not have a smartphone. Okay, and if you think about this, even though it's a different format than this top one, it's still the same equation. So if you add the probability of a smartphone plus the probability of not having a smartphone, it's going to equal 1. So 0.87 plus 0.13 equals 1. So we know that it's correct. All right, but like I said, usually you're just going to be using this second form of this rule when you're doing problems in your homework, quizzes, and exam. Okay, so hopefully that's not too bad. All right, so as we can see here in the slides, in the book, they did the same exact thing we did. And they got the probability of randomly selecting a household not having a smartphone is 0.13 or 13% chance. Okay, so next thing we need to talk about it's a big section, is the intuitive multiplication rule. So to find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B, but be sure that the probability of event B is found by assuming that event A has already occurred. Okay, that's a very long-winded way of saying that when they use the word and, you multiply the probabilities, which is why it's called the multiplication rule. The only thing they're warning us about is when you multiply the probabilities, you have to assume that event A has already occurred when you're calculating the probability of event B. All right, that's the intuitive multiplication rule. And then the actual formula is probability of A and B equals the probability of A times the probability of B given A. So this vertical line here means given. So this is the probability of event B given that event A has already occurred. And this is just how the math ends up working out for the formal multiplication rule. But we're going to talk more about this notation here because it's the first time we've seen it in our class. So for the multiplication rule, the probability of A and B means the probability that event A occurs in a first trial and event B occurs in a second trial. And then the new thing here is this, probability of B given A. So the vertical line, this vertical line means given. Okay, so like here, the probability of B given A represents the probability of event B occurring given that event A has already occurred. Okay, which might be a little bit confusing at first, but I did want to show you an example from our homework on how to use this. Okay, so let me see if the homework is still up here. Oh, my session has ended. Okay, well, so the one I wanted to look at was question number 2. Oh, good, it's still there. Okay, so this is a question from your homework, and remember that your homework is randomly generated, so the exact question on your homework might be a little bit different than the examples I'm giving, but they'll be similar. All right, so this is question number 2 on the homework that I'm putting up from 4.2. And it says, when randomly selecting adults, let M denote the probability of randomly selecting a male, and let B denote the event of selecting someone with blue eyes. I don't know why I said probability. I meant to just say event. Okay, so M is the event of selecting a male. B is the event of selecting someone with blue eyes. Now here they're asking us, what does probability of M given B represent? Okay, so that's their first question. Okay, so the thing is, probability of M given B, you can just read it. So that's the probability of M, which is male, given blue eyes. Okay, so probability of M given B is the same as probability of male given blue eyes. M given B means the probability of selecting someone given that we know they have blue eyes, what is the chance that they're male? Okay, so what is the probability of selecting someone who's male given that we know they have blue eyes, is what that means. Okay, so going back to this actual problem, we have to look at these. These are multiple choice. The probability of M given B represents the probability of getting a male given that someone with blue eyes has been selected. So that's choice D. If you look at choices A, B, or C, they're close to what I was saying, but they're not the same thing. Okay, the problem with choice A is it says the probability of getting a male or getting someone with blue eyes. So that would be the addition rule. So that's wrong. Choice B says the probability of getting someone with blue eyes given that a male has been selected. That would actually be the probability of B given M. Okay. All right, and then choice C is wrong is because it says the probability of getting a male and getting someone with blue eyes. We're not using the word and here. We're using this vertical bar, which means given. So P of M given B means the probability of getting a male given that someone with blue eyes has been selected. Okay. So hopefully that's helpful. And then they ask us, is the probability of M given B the same as the probability of B given M? And if you want to think about that for a second, pause the video, and then I will explain that to you right away. Okay, so the answer is no. The probability of male given that someone has blue eyes is generally not going to be the same as the probability that someone has blue eyes given that they're male. It's possible in some situations that they would mean the same thing, but only if the numbers just coincide, that they happen to be the same numbers. Okay, so the answer is no, because probability of B given M actually means the probability that someone has blue eyes given that we already know that they're male. Okay, these are two different things. Right, so it's possible in some situations that they would equal the same number, but they definitely don't mean the same thing. Okay. So let's see, looking at their choices, which of these looks like what we were just saying? So first of all, we know that the answer is no, right? So it's either going to be choice B or choice D. So if we read choice B, it says, no, because probability of B given M represents the probability of getting a male given that someone has blue eyes. Well, that's not true, right? The order is switched there. So choice B is wrong because it says probability of blue eyes given male, but they're saying the reverse here. They're saying the probability of male given blue eyes. So it's not choice B, which means it has to be choice D. So choice D says, no, because the probability of B given M represents the probability of getting someone with blue eyes given that a male has been selected. Okay? Cool. So that is question number 2 from your homework. And then we'll come back to this homework in a bit, but I wanted to return to the slides. So now we've seen the notation for the multiplication rule. And I want the camera to turn on. Okay, there we go. All right, so hopefully now we understand what this little bit here means. Now the thing is, with the multiplication rule, just like with the addition rule, there are certain cases where you don't even have to worry about this notation. Okay, so you don't even have to worry about the probability of B given A. Okay, in particular, if two events are independent, then the probability of B given A is just going to equal the probability of B. Okay, so two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. And then several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. If event A and event B are not independent, they are said to be dependent. Okay, so going back to the formal multiplication rule, if the events are dependent, we would use this format. But the multiplication rule, if the events are independent, well, if they're independent, then the probability of B given A isn't going to depend on A. So for independent events, then the formal multiplication rule just simplifies to probability of A and B equals probability of A times probability of B. Okay, it's the same formula as what we have up here. It's just if the events are independent, then the probability of B given that event A has already occurred, well, A doesn't make any difference because event B doesn't depend on event A if they're independent. So the probability of B given A is the same as the probability of B. Okay? So that's good to know. So as long as the chances of the first event A and the chances of the second event don't affect each other, we can just multiply the probabilities without worrying about it, which is very helpful because all the problems, or most of the problems, I should say, in your homework are independent events. So then this formal multiplication rule just says you multiply the probabilities as long as they're independent. Okay, so let's go ahead and talk about a little bit more stuff on the slides, and then I want to do a bunch of examples. Okay, so this is going to be a long video, potentially the longest video I've made in this class so far. I was thinking about splitting up into 2 videos, but I think we'll still be able to be at least under an hour and a half after we get done with all this. Okay, so I wanted to talk about this slide. I left it in here because it is important. Now, our book doesn't have very good problems for sampling, but I'm just mentioning this slide because you may need it at some point in another course or in the real world. So even though my math lab doesn't have very good problems, let's talk about this for this. So in the world of statistics, sampling methods are critically important. That is true. And the following relationships hold. Sampling with replacement means that the selections are independent, whereas sampling without replacement means that the selections are dependent. So because this doesn't show up on your homework, I'm just going to give you a really quick real-world example of this, because you might not be sure what this is saying. So if I have 4 markers, which I do here, and they're all different colors, okay? If I have 4 markers, then sampling with replacement means, say, if I put all these 4 markers into a bag, well, I don't really have a bag here. Well, I have my backpack, so that's kind of heavy. So we'll just say that we'll put them in this rag here. So I put the 4 markers in here. I scramble them. Sampling with replacement would mean I draw 1 marker, I see what color it is, and then the replacement means that I put the marker back into the bag, or in this case the rag, and then I shuffle them again, and then I draw another marker. That's replacement. So if you're putting the marker back before you draw the next marker, the selections are independent. And the reason they're independent is, so for example, the chance of drawing a green marker would be 1 out of 4 because there are 4 markers. Each one's a different color. One of those colors is green. Well, if I draw one marker, the chance of the first marker being green is 1 out of 4. With replacement would mean before I draw the second marker, I put the first marker back, I shuffle the markers again, and then I draw another marker. Wow, I got lucky, I got a green one. The only green one. Well, that's just saying that if you replace the marker, then the selections are independent events, because each time, as you can imagine, each time it's going to be a chance of 1/4 of drawing a green marker. What does sampling without replacement mean? Sampling without replacement would just mean that after we draw the first marker, we don't put it back. Okay, so sampling without replacement would mean, okay, well, the probability of drawing a green marker for the first marker is 1 in 4. Oh, this time I didn't get lucky here. Without replacement would mean I don't put whatever marker this is back. Well, then how many markers do I have left in my bag? Well, for drawing the second marker, I only have 3 markers left. So now my chance of drawing a green marker is going to be 1 out of 3. So without replacement, because I've already drawn a marker and I'm not putting it back, the selections are dependent events. In other words, if I happen to draw a pink marker for my first marker, then for my second draw, my chance of getting a green marker is 1 out of 3. Whereas, let's say, instead, for my, I gotta look now to get the green marker out. So if instead I draw a green marker for my first marker, well then for my second marker, what's the chance that it's going to be green? This is actually yellow. I know this one looks green in this lighting, but this one's actually yellow. Well, if I've already drawn a green marker, then my chance of drawing a green marker for the second marker is 0, right? Because there are no green markers here. Okay, so as you can see, without replacement, meaning that you don't put the marker back, the selections are dependent because the chances of drawing the second marker depends on which marker I drew first. Hopefully that makes a lot of sense. If not, we don't really have any homework questions on it. It's just an important concept that I wanted to go over real quick. Okay, and then I just wanted to summarize the addition rule and the multiplication rule, and then we'll do quite a few examples of, we're going to be focusing actually on tables for our examples. Okay, so addition rule, the word or means addition, and then when we're adding P of A and P of B, we have to avoid double counting. Okay, each outcome can only be counted only once. Multiplication rule, the word and suggests multiplication, and when multiplying P of A and P of B, we must be sure that the probability of event B takes into account the previous occurrence of event A. And of course, if the events are independent, then we can just do P of A times P of B. Okay, so that is all the slides. Now we're going to jump into examples. And for the examples, what I'm going to do is your homework problems, like I said, are randomly generated, so the numbers are going to be different from the ones I'm doing on here when you're actually doing your homework. So we're going to take a look at your homework, if it'll open up. There we go. Okay, so we already talked about question number 2, and then the other ones that I wanted to go over from your homework, obviously I don't have time to go over all of them, is question number 4. This one throws people off all the time. This one actually doesn't use the addition rule or the multiplication rule. This is actually the complement rule. Okay, so this one is asking us to find the indicated complement. A certain group of women has a 0.68% rate of red-green color blindness. If a woman is randomly selected, what is the probability that she does not have red-green color blindness? Okay, so the only thing that's challenging here that you might not know is because they gave us a percentage, we need to convert 0.68% into a decimal, which is a little bit confusing unless I tell you about it. So we have a 0.68% rate of red-green color blindness, but that probability is actually written as a percentage. Okay, so probability of, I'll just say colorblind for our event. It's actually the probability of colorblind given female, but we're just going to say probability of colorblind. We said that that was 0.68%. And the only thing that's confusing there is before we do the complement rule, we should probably convert this percentage into a decimal. So remember, if you're converting from a decimal to a percentage, you move the decimal 2 places to the right. However, this probability is already a percentage, so we have to go in reverse. So here, to convert this percentage into a decimal, we're going to move the decimal 2 places to the left. Okay, so the probability of colorblind is actually going to be, for this empty space, we put in a 0. Okay, so probability of colorblind here is going to be 0.0068. Now that's not what they asked for, though. They asked for the probability that someone is not colorblind. And these were all given to be women, so I'm not bothering to write given female because that's not really coming, it doesn't affect the problem. We just want to find the complement of colorblind. In other words, we can just write the probability of colorblind with a bar over it, horizontal bar, which means the probability that someone is not colorblind in this particular study. And then that's going to equal, using the complement rule, that's going to be 1 minus the probability that they are colorblind. Okay, so that's going to give us 1 minus 0.0068. And most people would want to do that on their calculator. But honestly, the only thing that was challenging about this problem was realizing that what they gave us was a percentage, and we have to convert it into a decimal before we use the complement rule. Because the complement rule is written for decimals. Remember, 1 is a decimal, 1.00. It's not a percentage. 1 as a decimal is the same as 100%. Okay, anyway, on our calculator, 1 minus 0.0068 gives us 0.9932. Okay, so 0.9932. And then because this is a probability, we would usually round this to 3 significant figures, so we would round it to 0.993 in most cases. But let's see what they asked us to do here for rounding. So if I return to the problem, it says type in integer or a decimal, do not round. Okay, so because it says do not round, we're actually going to type in the full number. So we're going to type in 0.9932. Okay, and that's the whole problem.